All right. So a sequence, by definition, is an ordered progression of elements, usually numbers. If a sequence consists of numbers, it is a discrete function whose domain is a set of positive integers, and each integer, each corresponding value is called a term of the sequence. So a sequence is made up of a bunch of terms written in a list. Now we can have a finite sequence, meaning the sequence ends. So in this first example here, we have 3, 6, 9, 12. And our sequences are always written in set notation, just like we sometimes write domain and range in set notation with those squiggly brackets. So whenever we have these squiggly brackets, that's what tells us set notation. Now, each term in the sequence has a position number, you can think of it as. So if we're looking at this finite sequence 3, 6, 9, 12, the first term, the term in position 1, is denoted as a sub 1. That's our first term in the sequence of a sub n. The second term is a sub 2. Third term is a sub 3. Fourth term is a sub 4. And then the final term is always a sub n. Or we can refer to the entire sequence as a sub n, the sequence a sub n, where n is the number of terms in the sequence, if it's a finite sequence. Now, there are two ways. Oh, I should say, there's also an infinite sequence, meaning it goes on forever, which normally there'll be like a dot, dot, dot written at the end of the sequence to tell you that it goes on forever. Now, there are two ways to do what is called defining the sequence, right? To write down an equation for the sequence. One is to explicitly define the sequence. The other is to do what is called recursively defining the sequence. So we're going to go over both of those ways right now. Now, the great thing about explicitly is you can figure out what any term of the sequence is, no matter what term you're looking for. So like you can find the 100th term, you can find the 1000th term. It doesn't matter, you can automatically find it. You can't do that so much with recursively, and we'll see why in a second. But explicitly, this first example, we have an explicitly defined sequence, and it wants us to find the first 4 terms. Now, all we have to do to find those first 4 terms, if we're trying to find term number 1, that means it has a k value of 1. All you have to do is plug in 1 for k. So 3 times 1 is 3, plus 4 is 7. That means the first term of the sequence is 7. And then we repeat. We're trying to find the second term, the position 2 term. So we plug in 2 for k. 3 times 2 is 6, plus 4 is 10. So the second term's value is 10. Then we plug in 3. 3 times 3 is 9. Plus 4 is 13. And lastly, it just wants to find the first 4 terms, so we plug in 4 again this time. 3 times 4 is 12. What was I about to write? I don't know. Plus 4 is 16. Then it asks, what's the 100th term? So this is the beauty of explicitly defined functions, or sequences. We can just take this 100th term and plug it in for k. That's 300 plus 4. The 100th term is 304. Now, Recursively defined sequences, on the other hand, always relate back to a previous term. You need to know a previous term to know future terms. Wow, my screen is really delayed. Oh, it said I lost network connection? There we go. Okay, cool. So this example 3 is written recursively. Notice it actually tells us in the notation what our first term is equal to, 32. It says b sub 1 is equal to 32. All right, so whenever you are recursively defining a sequence, you always have to state what the first term is, which they do here. They say b sub 1 is equal to 32. Meaning, if I'm writing out the terms of the, whoa, that's too many squiggles. If I'm writing out the terms of the sequence, my first term is 32. Then, we're trying to find the first 5 terms. So, I look at the rest of the recursively defined statement for sequence. It says that all of the other terms are equal to 0.5 times b sub n minus 1. Now this b sub n minus 1, what this means is, so if I'm trying to find b sub 2, I have to do 0.5 times b sub n minus 1. 2 minus 1 is 1. And we know that b sub 1 is equal to 32. So this is just 0.5 times 32. Whenever you see b sub n minus 1 or k minus 1 or anything minus 1, all that this means is the previous term. So 0.5 times 32 is 16. Basically, all of this fancy recursive notation, all that it's saying is multiply 0.5 times the previous term and you'll get your current term. So 0.5 times 16 is 8. 0.5 times 8 is 4. 0.5 times 4 is 2. And we found the first 5 terms. Does this make sense? I know it's a lot, and I know it's a lot of fancy writing. All we did was multiply the previous term by 0.5, or a half, to get the next term. All right, we'll do it again. We're trying to find the first 6 terms of this sequence, where it tells you a sub 1 is 1. Then we know a sub n minus 1 is the previous term. So we're taking the previous term, multiplying it by 2, and adding 3. So 2 times 1 is 2, plus 3 is 5. What do you think the next term is going to be? Yes, guys. Yes, 13, because 2 times 5 is 10, plus 3 is 13. Wonderful. What about the next one? $29. Good. And I'll just tell you, after that, it goes 61 and 125. Wonderful. So notice recursive is it's easier to find the first couple of terms, right? It's easier to find the first set of terms. But if I asked you, find the 100th term, you would have to find the 99th term to find the 100th term. Then to find the 99th term, you'd have to know the 98th. You'd have to know all of the terms to get to 100. That's why explicitly is easier to find higher terms. Recursively, it's easier to find lower terms. And you can write either one in either notation. It does not matter. All right. Any questions on how to, or the differences between explicitly and recursive definition? All right. So now we've gone over the ways that we can define sequences. Now we're going to go over two types of sequences, arithmetic and geometric sequences. Now, bottom line, an arithmetic sequence is when you add or subtract to get to the next term. Oh, it's not, there we go. The amount that you're adding or subtracting by is called the common difference, or D. If a sequence is geometric, what that means is you are going to multiply. Now, I'm not going to write divide here, because we always want to think of it as multiplication. But, you know, dividing by 2 is the same thing as multiplying by half. So if you notice something is just dividing to get to the next term, instead try to think of it as multiplication to get to the next term. So you always multiply to get to next term. And then we have some nice formulas for writing the arithmetic and geometric sequences. If we're trying to write it explicitly, an arithmetic sequence explicitly, this is the formula we use. If we're trying to write it recursively, this is the formula we use. But they didn't write it down. We have to state what a sub 1 is equal to. If we're writing anything recursively, we have to state the first term. We have to state the first term. Now, D is the common difference in an arithmetic sequence. R is the common ratio, it's called. It is the amount that you're multiplying by. Now, sometimes it's not so easy to find this value, the amount you're multiplying by. So what you can do, you can always take the second term of the sequence and divide it by the first term. This will give you the ratio that you're multiplying by to get the next term. Okay, so let's try it. First, we have to identify, is this arithmetic, geometric, or neither? It could be neither. There are a lot of sequences that are neither of these things. But let's look at this first sequence and tell me what's happening here. We are adding 7 each time. Exactly. Good. 5 plus 7 is 12. 12 plus 7 is 19. So, because we're adding to get to the next one, this is an arithmetic sequence. And it wants us to explicitly write this sequence. So I'm going to go up here to my formula, which tells me a sub n is equal to a sub 1, which is how much? 5. Right. Our first term, our a sub 1 is 5. Plus, what's our common difference? Our d? What's our d value? 7. Good. Times n minus 1. Now, Math Excel, unfortunately, Math Excel is going to want you to simplify this. How do we simplify, or how can we simplify this, do you think? How could I simplify this? Distribute the 7 in. So it becomes 5 plus 7n minus 7. And then what? What can you do? What can you combine? Ah, the 5 and the negative 7. So it becomes 7n minus 2. That's the simplified version in explicit notation for this sequence. Then it wants us to find the 20th term. So all I have to do is plug in 20 for n. 7 times 20 is 140, minus 2 is 138. Any questions? Whew. Okay, so let's try it again. What pattern do you recognize in the second sequence? This one's a little bit harder. Let me ask you this. Are you adding or subtracting by the same amount every time? Like to go from 9 to 12, I'm adding 3. But to go from 12 to 16, I'm adding 4. So this is not an arithmetic. I'm not adding by the same amount. Right, Keelan? So I need to check, okay, am I multiplying? Now, like I said, it's not so easy sometimes to see what you're multiplying by because you don't have to be multiplying by a whole number, right? To go from 9 to 12, we're definitely not multiplying by a whole number. But remember, I told you that you can always find a ratio by taking your second term and dividing it by your first term. 12 divided by 9 is 4/3. So we ask ourselves, 9 times 4/3, is that 12? Well, yes, it is. 12 times 16, I'm sorry, 12 times 4/3, is that 16? Whoops. Why is this so big? Oh, look at that. It is. Let's check one more time. 16 times 4/3. Is that 21 1/3? Oh, yes, it is. So, what type of sequence is this? It is geometric because I'm multiplying by the same amount. Good. Now it wants us again to explicitly write this rule, so I need to use this explicit formula. Whoops. A sub n is equal to, now what's my a sub 1 value in this problem? 9 times my ratio, my common ratio, which is 4/3, raised to the power of n minus 1. Now this is as simplified as this gets. We can't simplify this any further, so we're going to leave it like this. Then it wants us to find the 8th term. How do you think we're going to find the 8th term? What do you think we're going to do? Because this is explicitly written, what do we do to find the 8th term? Thank you, Sophia. Yes. We just plug in 8. Plug in 8 for n. So we have 9 times 4/3 raised to the power of 8 minus 1 is 7. 67, whoops, what was that? 67.42. So we have our explicitly defined sequence right here, and we have our 8th term right there. Any questions? Okay, we're not fully going to do C and D, but I do want us to identify, are these arithmetic or geometric? So in part C, what pattern do you see? Right, we're just adding 5 every time. So is this arithmetic or geometric? Yes. Meaning if I'm writing down my explicit rule, it's just going to be a sub 1 plus the common difference times n minus 1. Simplify this down, and I get 5n minus 2. All right, so then part D. What pattern do you see? Yes, Colin, exactly. We just multiply by 0.9 every time. Again, if you can't clearly see that, you can always divide the second term by the first term. So, is this geometric or arithmetic? Geo, good. And this time we do a sub n is equal to the first term, which is 1, times the ratio raised to n minus 1. Okay. So then, part E says for examples A and B, write the recursive rule for each. So we're now recursively writing it, meaning we have to always state what the first term is. So for A, our first term is 5. Then I write down the recursive formula. So I look up here, part A was arithmetic, so I'm using this formula. A sub n is equal to a sub n minus 1 plus d. So a sub n minus 1 plus d, and our common difference for part A was 7. So I just put plus 7. And boom, that one's done. Part B is geometric though. Our first term was 9. And I need to look at our recursive definition for geometric right here. A sub n is equal to a sub n minus 1 times the ratio. Our ratio for B was 4/3, I think, yes. Or, as it's more commonly seen, you would write 4/3 out in front so that you don't have to worry about parentheses. Are there any questions on these? So far, we've gone over two types of sequences, geometric and arithmetic. There's always neither. They don't always have to be arithmetic or geometric, but these are just the two most common types we'll see. And then also we've gone over two ways to write the sequences, recursively and explicitly. We're just going to do two more problems and then we're just done for today because this whole part V, part 5, 6, and 7 are not actually on your Math Excel. These notes will be filled out on my on Schoology, but you don't really have to worry about them. So let's just take a look at parts A and B here. These last two problems. Identify the pattern, write the next three terms of the sequence. So, what pattern do you see here? This one's tricky because technically it's not arithmetic and it's not geometric. It's neither. But what do you see is happening? What if I found how much we're increasing by each time? So this one's going up by 3. This one's going up by 5. This one's going up by 7. What do you notice? Ah, the difference is itself increasing by 2 every time. So technically, what I wrote in purple, that is called the first difference. If there is another row of differences that are the same, that are constant. So here we have another row of differences, which are called our second differences. Whoops, whoops. Oh my God. If these are constant, this is actually a quadratic. Now, can anyone tell me what my sequence's definition is going to be? We know it's a quadratic because the second difference was the same. But if if I'm trying to find the first term, so say I plug in 1 here. and I square 1. Is that what my first term is equal to? What do I need to do to this definition to force it, to force the first term to be equal to 2? What do you think I can do? Yes, Sophia, we just need to add 1. And that's what will make it be correct. So let's check here. If I'm trying to find the second term, I plug in 2. 2 squared is 4 plus 1. Oh, yes, that's 5. That's what I wanted it to be. If I'm trying to find the third term, I plug in 3. 3 squared is 9. 9 squared, I'm sorry, 9 plus 1 is 10. Exactly. So basically, on these problems where the second difference is the same, all you have to do is square your n and then look to see what needs to be done so that the first term is correct. Does that make sense? Okay, cool. Cool, cool. All right. It then wanted us to find the next 3 terms. So we ended on term 4. Term 5, when I plug in 5, 5 squared is 25 plus 1 is 26. 6 squared is 36 plus 1 is 37. 7 squared is 49 plus 1 is 50. This is a sub 5, a sub 6, and a sub 7. All right, one more and then we're done. Right here. Now I wanted to show you this one because again, it's not geometric, it's not arithmetic, it's not as easy. But I love it when I see fractions. As soon as you think of these fractions as 2 separate sequences, one sequence for the numerator and one sequence for the denominator, it actually becomes quite easy. So let's first define, let's see, which one's easy? Oh, my phone. Don't have cracked. Oh. Okay, we're good. So let's look at the denominator. Let's first define or try to define the denominator. What do you recognize about the denominator? This is my first term. This is my second term. This is my third term. This is my fourth term. What do you notice about the term position and the number in the denominator? What do you notice? They're the same. They're the same, yes. So, how could we define our denominator? What is that term position? What variable can I replace that with? Or have we been replacing that with? N, yes. The term's value is equal to n, the position number. Okay, so knowing that, how could we define the numerator? It is also increasing by 1 each time. What do you notice about the term's number versus what's in the numerator? It's not the same this time, but what do we do to the term number to get the numerator each time? Yes! So the numerator is just n plus 1. Meaning, my fifth term is going to be 6 over 5. My sixth term, 7 over 6. My seventh term, 8 over 7. And I'm done. Are there any questions? about anything. All right, guys. And that's all I have for you. You do have an 12.1 homework, okay? And if you didn't do the test, you need to do it by Friday as a retake.